Yesterday we looked at parametric equations. When you do a parametric equation of any graph, it's called a parametrization. Okay, kind of an odd word, a clunky word. But we can parametrize a line or a circle or an ellipse or a parabola. We can do any of those as parametrics. Okay, and we're also going to look at slope. Okay. Slope is still going to be y over x. And you just have to do the parametric version of it. Figure it out from the parametrics. Okay, so again, parametrics is shape based on time, right? So we have direction and time. If you want to parametrize a line, okay, the x is, and this line is through a point, AB, and then the slope of the M is going to be S over R. Okay. So those are your two, your X and Y coordinates are generated from A and B, and then the slope is generated from S over R. Just like we would always do the Y's over the X's, right? Y's over R. Okay.
So it's just like y equals mx plus b for both equations?
Yeah, you can turn this totally into a y equals mx plus b equation. Same format. So if I have, let's say I have a point and a slope. And parametrize that line. So we would say something of that nature, right? Obviously A and B, right? What can S and R be? Any variation of that makes 4, right? So obviously the easy one is 4 over 1, yeah? But can you think of any others? 8 over 2, 12 over 3, negative 8 over negative 2. You can use any combination of those you want, and it makes the same exact line. Okay, so any line has an infinite number of parametric equations, right? So just keep that in mind. So what's this? 3 plus t, and y is negative 1 plus 4t in this case, right?
That's all you have to do to
Parametrize a line. Yeah. Now sometimes you're given 2 points, right? You'll have to calculate the slope and use one of the points. That's okay, right? There is a parametrization of a line using 2 points, but I don't see the point in memorizing it, because you can always just use this, right? So, and again, I can also write S over R as anything I want. So, okay, those are the same line, right? Doesn't matter, because when you calculate the slope, it comes out the same. All right. Good. All right. Let's talk about surface. What's the most famous circle in the world? Or the one that we use the most, I should say.
Unit circle?
Yeah. Okay, so the unit circle.
I was going to say, like, I don't know when you want to
No, there are an infinite number of circles.
Yeah, but
There's just the one we use the most, right? Okay, so what's the radius of the unit circle?
1.
Okay, and then how do I generate any coordinate based on the angle? Hmm? Yeah, cosine and sine, right? Okay, so the parametrization of a circle uses that information. Okay. Because time is a real number, correct? And the angles that we use in calculus are radians, right? Which is a real number. So really what you have here is the angle is your time component, right? Because and okay. So we can write this actually as cosine t and sine t. Okay, that's the parametrization of the unit circle. Right there. Okay. It's kind of funny to think about time being an angle, right? But they connect really well because these are both real numbers. Okay. But that's with radius 1. What if I want the radius to be something different? Can you think of any way to add that into this parametrization? No? It's pretty, if you have any radius. All you do is multiply by r. So in our case, it's 1, right? So we don't have to worry about it in the unit circle. Okay.
Oh, so that's just for, that's how
It says
you
any radius.
parameterize any circle?
Any circle. Where's this circle centered?
0, 0.
Yeah.
Okay.
All right. So that's a circle centered at 0, 0. And then you can take it one step farther. What if the center is AB?
Just add AB first, right?
Yeah. So we have A plus R cosine T, B plus R sine T. Okay. So this is, I mean, obviously the generalization, right? Because you can move the circle anywhere and it can be any size at that point. Okay. Your book actually does list this as theta, as an angle. Okay, but it's the same thing. Do you want to see one graph? Or do you think that's enough?
I'd like to see that.
Okay, so we'll just have to make one up then. So, it's a possible circle.
Definitely one. But not of course.
Yeah, ours have to match.
I thought
Yeah.
it was one.
Where's the center? Canyon? Yep, 2, 3. What's the radius? so 1, 2, 1, 2, 3, 4.
So when graphing these, you're not really looking at the cosine or the sine a whole lot.
No, you don't need to.
No, you're not.
Yeah,
You can do like that.
pretty much. Yeah. Yep.
So, do you ever have to find like a value based off the parametrized equation? Like, will it ever say like t equals something?
At time 2, what is the value of?
Okay.
Yeah. It's at that point, it's if this is not a unit circle value like pi or 3 pi over 2, it's just going to be a calculator problem. Where you might run into it is calculating slope. Okay, so you're okay with the circle?
Yeah.
Pretty straightforward, right? So calculating slope in a parametric curve is it's still a derivative. Okay, so the slope is always, in anything we do, parametrics or polars, vectors, it's always dy dx, right? Because that's what we've always done for slope. And we're still in an xy coordinate plane.
Right.
Okay, the question is, what is dy in a parametric curve? And what is dx in a parametric? Okay. Any ideas?
Wouldn't that be a lot harder to get because you're using to define those two values?
Yeah, so if you're deriving y, what with respect to what? T. Yeah.
So you have to do
So it's dy
over
dt,
and dx over dt?
dx dt. Now if you have your fraction division, what happens to the dt's? They cancel out, right? Okay, but if we're in this circle, what's dy dt? Or cosine t, right? And the bottom is -4 sine t. So, and at this point, you might be asked, what is dy dx at t equals pi? That's a bad one, over 2. Well, that's just 4 cosine pi over 2, and -4 sine pi over 2. Right.
Oh, we can go back up. Okay, so how did you get dy with 4 cosine?
This is the y component. Derive it.
Oh, that's what you.
Yeah, so 4 derivative of sine is cosine, right?
Okay, yeah.
Yeah, and then you have negative sine here. You guys good with that? Okay. All right, so if we're evaluating at pi over 2, you're asking at time pi over 2, what's the slope of a line on that circle? Okay, so the 4's will cancel, we don't even need them. Cosine of pi over 2 is 0. Doesn't even matter what sine is, but so same location, pi over 2, horizontal tangent line, right? So this falls right in line with your unit circle, or you just have to put it in terms of t. So, all right, I think we're good there. How about an ellipse?
Are they as straightforward as circle?
Do you remember the ellipse equation from pre-calc?
I do not know.
I didn't
Not
think
in
so.
slide.
And I only mention it because it pops up now and again. I don't for some reason.
Isn't it x minus center squared over the radius of the x?
Yeah, but we're just going to worry about centered at 0, 0 for now.
So it's just
So-
x over x squared.
X squared over radius of x plus y squared over radius of y equals 1.
1, yeah. Okay. So that's it, the ellipse. Remember, major axis is the A value. So this would be an ellipse with the major axis that's in the x, minor axis in the y. Okay, so I mean, just a little refresher there. A and B come from here and here. Okay, so and then
And why is it b squared?
That's your radii.
I don't think that was thinking.
Or not to
no. If these are the same,
because the three equations.
what shape do you have?
Circle?
A circle. And a circle is r squared, right? So it has to, this is not a great explanation, but if these are the same, they have to be squared. That's like the radius of a circle, right? So the radius of a circle squared, if you brought it down below, it would be r squared and r squared, but they have to be different to make an ellipse.
So it's just like that.
An ellipse is just a modified circle, in effect. You've stretched one of the axes, right? If you want to parametrize an ellipse, it's just like a center of or just like a circle centered at 0, 0. The only difference is that these are different, right? That's it. Okay. We do have a bound on this. And it escapes me why. But again, if you go through, just use your unit circle values, you can plot that. Or you just know A and B, recognize it. A and B give you these lengths here, and you've got yourself an ellipse. Okay. Do you want me to plot one of those two, or good? Okay. Again, you know what A is? So that's each side of the center. You know what B is? Each side of the center. Done.
So if it's centered at like 1, 5, the center of the plus A.
Now, how do you
It would, yeah, if it was centered somewhere else, it'd probably be some value plus this and some value plus that. But we don't have it here. I don't think they're going to worry about it on an AP exam, to be honest with you. But it's just like a circle, right? So if you know how to do a circle, you pretty much know how to do an ellipse. Just modify that one little value. Okay. What's the slope of any tangent line on an ellipse? What's the derivative of the y? B cosine t. And negative a sine t. Okay. Again, it looks just like a circle, except for these values will be different now. So
facilitate the AV problems.
AB. Oh, calc AB problems? Yeah, if you want to. Yeah. Yeah, there's no restriction on what type of work you use if you can solve an equation or a problem. So, okay. So we've done line, circle, ellipse. Okay, those are the main three. The last one that we need to look at is called the cycloid. This is where we want to spend some time. Okay. It is kind of a funky shape, but it has some really interesting properties. A cycloid is formed by using a point on a circle. When you rotate the circle, that point traces out a shape. Right? So, see that point there on the circle is tracing this curve out. Right? This is going to be a cycloid in the end. So at 2 pi, that radius of this circle is 1. So 2 pi is where this is going to hit the x-axis again. And you've got an arc here, right? I wish I could see this better. But then it's going to hit the x-axis, it's going to bounce back up. So it's just making little arches, right? That's called a cycloid. Okay, a cycloid can be stretched or shrunk horizontally and vertically, just like anything else that we have. Okay. I wish I had a better one.
Are you gonna ask us about these, or you just show it?
I do once in a while, that's why I'm showing it to you. You can see the motion just creates a bounce effect, right? You can change the value of where this dot is. And so I can actually see if this dot is still based on the circle, but if it's outside the circle, it's going to create a smooth curve. And if I bring that dot inside, it creates a smooth curve as well. If the point is on the circle, it has a cusp. So, what is a cycloid's parametric equation? Whoops. X is RT minus R sine t. This is where you have to be cautious because it's kind of backwards. The X is with the sine. And the Y is R minus R cosine t. All right.
It's not RT.
No. Yeah, pretty much. We're trying to make things difficult on you by switching the sine and cosine with the X and the Y, and then leaving out the T, just for fun. usually what they'll say is, you know, here's an equation, here's a parametric equation.
Solve it.
You know, what shape does it make and what's the slope of a line at t equals pi, right? Or something of that nature. But don't get real difficult into it. Trying to think where they've asked it in the past. And I can't think of any off the top of my head. So, an example might be that's a cycloid. What's the radius of the circle that this is based on? Yeah, so the radius is 1. And we could graph it. So just thinking through this, at time 0, where's that cycloid located? Parametric. Time 0, what do we have here? 0 and 0. Okay, so what about pi over 2? We have pi over 2 minus 1. Yuck. Correct? And this would be 1 minus 0. So what's pi over 2 minus 1? Like 0.5? Okay, and then we can go to pi. This is pi minus 0. And this would be 2. But you can kind of see the cycloids starting to form, right? If you go to 3 pi over 2, what do we get? 3 pi over 2 plus 1. Is that right? 1. So where's 3? That's almost 6.
I thought it started with 2 pi.
I would have thought that too, to be honest with you.
Also, when we do
Well,
2 pi,
it will actually, but your x component is not 2 pi. So if I put 2 pi here, what does this give me? 2 pi minus 0. Right? And I guess it is stopping there, and this would be 0, right? Boom. And there's one arc of your cycloid, right? Maximum at time pi, we would suppose, right? How would we find a maximum on that cycloid?
Can't you prove it through the table if it is?
Well, what if it's like right here? We don't know that just because we guess pi that's the highest number on our table doesn't mean it is the actual maximum.
Why go with what?
You can just do the first derivative test.
Derivative, set it equal to 0, just like always, right? So
But the y goes from increasing to decreasing, can't you say that's an maximum?
yeah, but you don't know what happens here or here. I think you're probably right. Yeah, it looks like we're probably right based on symmetry. but we need to justify our answer with the actual calculus, right? So that we know we're right for sure. So the derivative of y is positive sine t, right? That goof there. And what's the derivative of the x?
Negative, wait, 1
Minus
minus
cosine t. Set that equal to 0. Do we even need to worry about the bottom? So where is this critical point? T is 0. Or pi, or 2 pi, right? There's the one we probably want to focus on. Yeah, so do your sign analysis. Dy dx at pi over 2. And you do your dy dx at 3 pi over 2. You're going to get a negative and a positive because the slopes are, right? So we do have a maximum at pi, right? The derivative of pi over 2 is 1 over 1, positive. At 3 pi over 2, it's going to be negative. So, but again, all the same calculus you know applies here. Okay, so
I have a question.
just have it in your mindset. A maximum, oh, that means derivative equals 0, sign analysis, right?
I don't think there's actually a slope at the 0 or 2 pi.
No, there's not.
Yeah.
In this case, there would be a cusp. Like there would be no slope, right? Because this would bounce back up.
So what circle is going to generate a curve that's that long and not equally tall?
That you want a shorter curve and not as tall, is that what you're thinking?
Yeah.
Well,
doesn't
just
seem
change
like-
the radius.
Well, right, but like how could a circle generate that? That's really confusing to me.
Well,
'Cause, like, I mean, I know that you're
the circle,
rotating a circle, but
yeah, so you start, it's just a point on a circle. It's like a rolling wheel on a highway.
right.
Yeah, so when you rotate this circle, when it gets here, the point's there. Right, so you're just rotating this circle. And eventually this point will end up back on the ground, like a tire, right?
Right.
Okay. So, and this, if this radius is 1, how tall is the cycloid going to be? 2 units, because the diameter of the circle is 2, right? So, yeah, there you go. And if the radius is 1, what's the circumference of that circle? 2 pi r, right? That's where you're going to hit again on the x-axis. So all that works geometrically. It all just kind of meshes very nicely. All right. Okay, that's all.
Cool.
Do you need me to write the work down again? Take 5 minutes?
Go ahead.
It's just a lot of numbers.
It'll take me 5 minutes to get my output out and get to the right page.
If you ever do.
Right.
Does anybody need me to write it down? Did you say sure?
I wasn't here yesterday.
Oh. Okay. Do you understand what a parametric is? Not really.
It's a lot easier in series.
Yeah, you missed kind of an intro to parametrics yesterday.
That too?
Yep.
I'll see you later.
That's a bonus point if you want.
Mom could eat with everyone to the state this year.
I smell state title.
Oh, can't remember.
So the number 1 team's not gonna win state, huh?
That's a big upset.
That's huge. Because Moffat was the 8th seed then.
Alamo lost to Clayfield.
They were the 2 seeds?
Theory got stopped.
Welcome to the state tournament.
Boys, that's fine.
Never a guarantee.